Pythagoras' theorem is a special rule that applies to the three sides of a right-angled triangle. It is an equation that relates the three sides of the triangle to each other. If we know any two sides of a right-angled triangle, we can use the equation to calculate the other side. The right-angled triangle shown has sides of length A, B and C. Notice that C is the side that is opposite the right angle. This is called the hypotenuse and it is always the longest side. The equation is c squared equals a squared plus b squared. We can show this by drawing a square on each side of the triangle. The square on side A has area a squared, the square on side B has area b squared, and the side on square C has area c squared. The equation tells us that the area of the large square on the hypotenuse is equal to the sum of the areas of the two smaller squares. But remember, this only applies to right-angled triangles. We can rearrange the basic formula to find any side if we know the other two. To find side C, we simply take the square root of both sides of the equation. So C is equal to the square root of a squared plus b squared. To find side A, we first swap the sides of the equation. Then we subtract b squared from both sides, giving us a squared equals c squared minus b squared. Taking the square root of both sides gives us a equals the square root of c squared minus b squared. We can find b in a similar way. B equals the square root of c squared minus a squared. If we know two sides of a right-angled triangle, we can find the third side by using one of these three equations. Remember that C must be the hypotenuse. Here is a simple example. Side A is 3 and side B is 4. Since we are trying to find side C, we must use the formula for C from before. Substituting the values of A and B gives us C equals the square root of 3 squared plus 4 squared. 3 squared is 9 and 4 squared is 16, so this is the square root of 9 plus 16. That is the square root of 25. 25 is a perfect square. Its square root is 5 because 5 times 5 is 25. So the side C is exactly 5. We can visualize this by drawing squares on the sides A, B and C like we did before. Since we know that side A has length 3, we can divide the square on that side into 9 smaller squares, each with a side length of 1. Side B has length 4, so we can divide that square into 16 squares, also with a side length of 1. Side C has length 5, so we can divide that square into 25 squares, also with length 1. All of the small squares are the same size. If we take the 16 squares from side B, then add the 9 squares from side A, we can see that this creates a square of exactly the right size to match side C. In this example, we have a triangle with side B of length 2 and side C of length 3. We would like to find side A. We need to use the formula for A from before. Substituting the values of B and C gives us A equals the square root of 3 squared minus 2 squared. That is the square root of 9 minus 4. So side A is the square root of 5. That is approximately 2.2361. But if we want the exact answer, we need to leave it as a surd, root 5. As we have seen, when we calculate the sides of a right-angled triangle, the sides are sometimes all exact integers. 3, 4, 5 is one example. 5, 12, 13 is another example. There are many other examples. These sets of numbers are called Pythagorean triples. Not all right-angled triangles are like this, as we saw in the last example. Even if two sides are integers, the third side will often be a surd. We will look at a final example. This is a triangle where the two sides A and B are both of length 1. This is quite an interesting case because the triangle is actually half a square. In this case we can find the length of C directly without using Pythagoras. Let's draw squares on each side as before. The square on side A can be divided into two triangles that are both congruent with the original triangle. Congruent means they are exactly the same size and shape. The square on side B can be divided into two triangles in the same way, because of course it is the same length. The square on side C can be divided into four triangles. Even without using Pythagoras, we can see immediately that the square on side C has twice the area of the square on side A or B. Since a squared is 1, c squared must be 2, so c is the square root of 2. We could obtain the same result using the Pythagoras equation, of course. If you enjoyed this video, please subscribe or visit graphicmaths.com. The link is in the description below.